Arithmetic algorithms for hereditarily binary natural numbers. This talk is about an alternative numbering system that's motivated by some limitations of the conventional polynomial notation for numbers, and despite of being a very resilient notation that stayed essentially the same for the last 1000 years, our usual binary arithmetic makes little effort to take advantage of the structural uniformity of the operands when present. So computations are limited by the size of the operands or the results. And what we are trying to do here is about how we can do better if the structural complexity of the operands is much smaller than their bit sizes. Not for all the numbers this happens. It happens for a few, but very important ones, and then the complexity gains will be arbitrarily high, actually. So our outline will go over notations versus computations for giant numbers, specific canonical representation of numbers called bijective base 2, then hereditary binary numbers, our main representation, and some operations on them, starting with successor and predecessor, then emulating doubling and halving in terms of base 2 operations, and some of the corresponding notations, the usual arithmetic operations finally, and the structural complexity, an analysis of what we gain and what we don't gain with this number representation, and then our conclusion. So notations versus computations with giant numbers. Notations like Donald Knuth's upper or tetration are useful in describing very large numbers, but they do not provide the ability to actually compute with them, as addition or multiplication results in numbers that cannot be expressed within the notation. So this is not closed under the usual arithmetic operations. So what we would like to show you is a novel canonical numbering system that allows computations with numbers comparable in size with the Knuth upper notation. These computations have average and worst case complexity that is comparable with the traditional binary numbers, but their best case complexity outperform binary numbers by an arbitrary tower of exponents factor. Hereditary number system is based on applying recursively run length compression of bijective binary digit notation. And to evaluate the impact of that notation and the computations with it, we discuss a concept of structural complexity that serves as an indicator of the expected performance of our arithmetic operations. So let's start with bijective base 2 numbers as iterated function applications. We have two functions, O of x, which is 2x plus 1, and I of x, which is 2x plus 2. They kind of stand for O, meaning our 0 notation, and I, our 1 notation. And they are called bijective base 2 representations because they represent every number canonical. Zeros in that case count, and natural numbers are simply iterated applications of those two functions. We have a few of them here. 0 would be just no application at all. 1 would be application of a 1 O on this 0. 2 would be an application of an I, then double applications of O, and so on. So if we look at O and I as binary digits, we see that all combinations are valid so the complete language of 0, 1 star is actually used to represent numbers, including the empty sequence epsilon. We get some nice properties of the iterated functions O at n and I at n, so applying O n times and applying I n times. The first one is that the successor of O at n applied to the predecessor applied to k, k is a number, is the same as the left shift operation, k times 2 at n, so left shifting k with n position. And then the double application of the successor at I at n applied to the double application of predecessor to k also works like the left shift operation. And this is easy to prove by induction, and this is also in the paper, so I will skip that. Rewriting those as conventional mathematical notation gives us the following two very useful identities. They connect O at n applied to k with 2 at n times k plus 1 minus 1, and I at n applied to k would be 2 at n times k plus 2 minus 2. So it's just a rewriting in conventional mathematical notation of the previous proposition. And in particular, we have application of the iterated functions O at n to 0, giving the exponent of 2 minus 1, and application of I, exponent of 2 at n plus 1 minus 2. We'll use them when we'll engineer our arithmetic operations. So the representation now, hereditarily binary numbers. We call them hereditarily binary because this idea of binary notation is applied at each level. When we count how many O symbol and I symbols, or zeros and ones, exist in a given representation, we actually represent that over and over by designing them in binary rather than working on each zero one at a time. So that's why they are hereditarily binary. The numbers can be expressed by this hereditary, by this data type in Haskell, data type T, which can be read as follows. An object of the data type T is either the empty object, or it is the V constructor followed by one object of type T, and then a list of objects of type T. This notation means at least one branch for this type of tree, and the same applies for W, the constructor W, at least one application, one T object, and then a list of T objects. Deriving equality read and show, it means that Haskell derives for us automatically the equality operation. It provides a parser and it provides a printer for objects of this type. So if we go over this again, the term E, which would be an empty list of this tree representation, the data T represents trees that are kind of colored with the constructors V and W and having leaves of type E. The term E corresponds to 0. V x-axis counts the number x plus 1 of O applications followed by an alternation of similar counts for I and O applications. And we start at 0, so we have x plus 1 of them to count. And the same thing is applied for W, which starts with I applications followed by an alternation of similar counts of O and I applications. The same principle is applied recursively for the counters until the empty sequence is reached. If we put this all together into a closed formula, we get a function from trees of type T to natural numbers that goes by case analysis. So it is 0 if the argument is equal to the empty leaf, if the argument is a constructor of type V, and then nothing after that except one other object, then it would be 2 at nx plus 1 minus 1. A little bit more elaborate in the case when we have a non-empty set of alternating O and I blocks. The computation works both on those terms, so we have 2 calls to n recursively here, and the same applies for W terms, kind of symmetric what's going on here. And the example shows you the computation for a very simple term, W of V empty, and then a list of 3 empty leaves here. This expands to this computation that ends up being 42. So the first natural numbers with this notation, we can verify this by applying the formula, would be 0, then 1, 2, 3, 4, 5. They correspond to relatively small trees, as we can see. So the main result here is that n is a bijection. Each term canonically represents the corresponding natural number. We'll also provide a construction of the inverse in one of the next slides, and that would highlight what's really going on with this bijection between trees and numbers. But let's now see the mutually recursive successor and predecessor. The successor is defined also by case analysis. By case analysis on the empty list, the empty tree, objects of type V and objects of type W, and the predecessor S prime corresponds, kind of reading right to left, one by one, to the same computations as the successor, but performed backward. And they're one inverse of the other. Easy to prove by structural induction. The recursive calls to S and S prime in S and S prime happen on terms that are logarithmic in the bit size of their operands. So the worst case complexity of S and S prime is given by the iterated logarithm of their arguments, how many times the logarithm can be applied until we reach 0. And this can be seen very clearly here. Each time we look at one application of S, we can see that the term on which S or S prime is applied when called from S is always a subterm here, and those subterms are logarithmically smaller than the actual argument to which the operation is applied. And the same happens with the predecessor operation S prime as well. So that gives us a worst case complexity, but somewhat more surprising is that the average size of a block is 2 bits. That's very easy to prove, see the paper. Therefore, the average time complexity of S is constant, and of S prime as well, of course. Experimentally, this is confirmed on all the numbers up to 230, but also on random numbers of 5,000 bits, and the average is 2.21 calls per successor and predecessor computation. So once you get to a 2-bit block, then you might or might not have one more call, and that explains this maximum of 225 actually, 2.25 that you can have in terms of number of calls of S or S prime from S or S prime. So that kind of handles the complexity of successor and predecessor. And now the interesting part is that the bijective based two operations, the constructors O and I that apply 2x plus 1 and 2x plus 2, and their inverses O prime and I prime, they can also be expressed, as we can see here, by calling S at most once, and the same thing applies for O prime and I prime by calling S prime at most once. So their complexity is the same as S and S prime, and those operations compute 2x plus 1 and 2x plus 2, so they are providing doubling, so multiplication operation, and they're still in either constant average time or log star worst case complexity. The recognizers are constant time. They just detect the empty and detect the odd numbers actually. That's interesting to see that, of course, because this starts with application of a 2x plus 1, then V constructor corresponds to odd numbers, and an I application corresponds to even numbers because it starts with a 2x plus 2. Even numbers or odd numbers that are larger than 0, so we can have a structural classification of those trees into empty or odd trees corresponding to odd numbers, or trees corresponding to even numbers. So the inverse bijection now is relatively easy to build. We have T of x, that is the empty leaf for x equals 0, and then applying numerically the inverse of O here, and then applying O over it, applying numerically the inverse of I here, and then applying T, and then applying the 3 operation I here. So the composition of this and the n operation gives identity in both cases, and this is relatively easy to compute and prove by structural induction, and this actually provides constructively the inverse bijection from n to t. So a few more low complexity operations can now be introduced. The double would be just the predecessor of O, because O is 2x plus 1. Half would be O prime composed with S, that's just the inverse of this. And then more interestingly, exponent of 2 is also a constant time operation that applies an S and an S prime at most. So we get doubling, halving, and exponent of 2, still average constant time, and worst case log star, which is very nice properties for those fundamental operations. Now, if we go further, and we'll go a little bit faster over the actual arithmetic operations, but they are detailed in the paper, which is a literate program at the same time, so everything in the paper can be tested in Haskell. The arithmetic operations working one block at a time favor numbers that have relatively large blocks of O and I applications, kind of corresponding to having large blocks of 0 and 1 digits in their corresponding binary representation. And in this case, we start by implementing in Haskell the on and in block operations, using those operations. And we can see here that we use an add operation that we'll define later. So we end up with a chain of mutually recursive functions, actually, O times I times, then various helper functions, addition, subtraction, comparison, and bit size. And they all form a relatively intricate network of mutually recursive functions, but this is manageable as they all progress on structurally smaller terms. So all our computations terminate and collaborate together to work exclusively in terms of tree operations. We don't borrow anything from conventional arithmetic operations in these algorithms. So to do addition, we use a few arithmetic identities that express what's happening when a block of k O digits and another block need to be added up. Well, this is a very simple thing. It would be an I at k, and then recursively we still have to add up x and y, but we progressed, we eliminated this block and that block, and now we only have to handle the remaining part of the two numbers. And the same applies when we have a different combination, slightly trickier formula, but not much, and the same applies also here. So this becomes Haskell code, and the details are a little bit more tedious here, but basically we implement those formulae and then the appropriate case analysis depending on detecting if things are odd or even. Subtraction works very much the same way as addition. We have a few arithmetic identities and then the corresponding Haskell code designed based on those. Somewhat more interesting is comparison, which provides a total order on those trees. Equality comes for free. We could derive it because the structural equality, two terms are equal if and only if they have exactly the same structure. But to see that one is smaller than another, we need to recurse over their structure and see it. Fortunately, if their bit sizes are different, we know for sure which is bigger. For bijective base 2, because zeros and ones both count, basically if the bit size of a number is larger than the bit size of another one, then the number is larger. So we only have really to compare numbers that happen to have the same bit size, which is the case here. And in that case, we proceed and we have to reverse the numbers because comparison proceeds from left to right. The leftmost digits are dominant, but our representation goes basically right to left, from smaller digits to larger digits. So the functions reverse dual that are in the paper will show exactly how that goes. Finally, bit size. It's relatively easy to compute. It only uses addition. Basically, we add up the sizes of all the blocks that we have, and that gives us the bit size. So because bit size also uses add, and we have seen in the very beginning that other things use bit size, this concludes the chain of our mutually recursive functions that cover basic arithmetic, addition and subtraction and comparison, basically, and bit size. Other operations come as another layer. For instance, we have fast multiplication by an exponent of 2 here, and in the paper we also have fast division by an exponent of 2 corresponding to right shift. So we are ready now to look at structural complexity. We define a function called t size that counts the nodes of a tree of type T except the root, and it focuses on the internal nodes only and ignores the leaves. So this function is 0 if T is empty. Otherwise, it would be 1 plus the complexity of all the components that it has, depending if it independently if it's a V or a W type of node. And with this definition, we get that the structural complexity given by the Haskell function t size is smaller than bit size. The actual function is here, and what we get is that for operations like S, O, I, and exponent of 2, the worst case effort is proportional to the depth of the tree that would be measured by the iterative logarithm. But the depth of the tree is proportional to the height of the corresponding tower of exponents, so we can handle very large numbers here, provided they are structurally simple, they do not have too many nodes. So the limit becomes the number of nodes in the tree rather than the bit size. For operations like add, sub, and comparison, worst case is proportional with the tree size of the smallest operand, typically. So each time when structural complexity is smaller than bit size, we gain. But as it is always smaller or equal, we never lose, of course, except by constant factors which come from the underlying implementation of trees versus bit string arithmetic. So in the best case, we can gain by an arbitrary tower of exponents factor, especially when we have very tall trees. And we have a picture here where the upper green line shows you the bit size of numbers up to a 10 minus 1, and then the red line here shows various structural complexities or tree sizes. You can see that in the lower part here you have relatively interesting numbers corresponding to towers of exponents of 2, small towers in this case up to a 10, of course, and then also linear combinations of them. This is kind of a repetitive self-similar structure, and it goes like that for very large numbers in a very similar way. Of course, there is also a case for some numbers close to random numbers where the bit size and the structural complexity are the same. Our structural complexity is just a weak approximation of Kolmogorov complexity, and as such, the majority of numbers being random, we do not gain on a majority of numbers. But what we do gain is we gain on relatively few but potentially interesting numbers that are below this bit size significantly, possibly by a tower of exponents factor. So our best and worst case corresponds to actually having a tower of this form of applications of W that gives 65,000 something versus a bit size that would, so the bit size in this case would be 15, but the term size, the tree actually here, would be only 3, so that's a clear best case, and the taller the tower, the bit size goes very fast, and the term size would stay proportional to a number of nodes, so relatively small. The worst case when we have a lot of empty leaves, a relatively flat tree, and in this case the bit size and the term size identical, we don't gain anything in this case. Large numbers allow structural complexity. Some of them are actually quite famous. We have the largest known prime number here, that's very large to display on paper with bit string notation, but which has this very small or comparatively small structural complexity representation in this directed acyclic graph that folds together the leaves of the tree, a lot of empty leaves here all folded together, just to provide a more compact representation. We can see the nodes marked by V and W, and at the same time we can see the 0 and 2 and 3, the number of the numbers on those arcs indicating the position in the list of children of a given node. Very compact representation for this very large number. Also, most of the record holder prime numbers, besides the Mersenne ones, have similar very small representations. We don't have room for that in this paper, but in a follow-up paper we'll go over that in full detail. So some of the future work, Sophie-Germain primes are important for being a special case in Fermat's theorem, actually, that was proved about 100 years ago for the spatial case. So P and 2P plus 1 are primes. If you put them together to form a sequence, then you get Cunningham chains. So they are just Sophie-Germain primes, but chained together. An example of such a chain is 2, 5, 11, 23, 47. So 2 times 2 plus 1 is 5, times 2 plus 1 is 11, times 2 plus 1 is 23, and so on. They can be seen as iterated O at K operations, actually. So this brings us to a surprising potential application, prime coins. That's a digital currency similar to bitcoins that mints Cunningham chains using Fermat's pseudo-primality test rather than using the one-way hash functions that are used in mining bitcoins. So what we notice here is that all members of a Cunningham chain are of this form. They are V, K, XS, and K plus 1 XS, and so on. So they are kind of specific representations using our notation, and they have a lot of subterms to share. So definitely a compact representation is possible for storing Cunningham chains. It's also very interesting to see if some computations for finding such chains, especially very large ones, are easier by using our operations than conventional arithmetic, but this is an open question. Another open question is, can our tree-based numbers benefit to modular arithmetic operations important in cryptography? And there is work in progress going on adapting Lucas-Lehmer spatialized primality test and the Miller-Rabin probably prime test to our numbers. So in conclusion, we have shown that computations like addition, subtraction, exponent of 2, and bit size can be performed with giant numbers in constant time or time proportional to their representation size or structural complexity rather than their bit size. While this is an approximation of Kolmogorov complexity, it's still important that Um, some of the best cases are very popular numbers like record holding primes, and we could say that like humans in a random universe, best cases are important, even if they're comparatively few, based on the Kolmogorov complexity reasoning. Uh, anyway, our code is available at this link here. And we have also Scala-based open source project replicating more or less the same at this Google Code site. Thank you.